Thank you, Andy. Hi, everyone. Thanks for being here. My name is Elba Alonso-Monsalve, and I'm a grad student at MIT, my final year. And today I'm going to tell you about a fun project that I did with Daniel Harlow and Patrick Jefferson, along with some details about upcoming work that will come out later this week. So a problem that I think a lot of us are interested in is how to do quantum gravity, how to apply quantum gravity to our entire universe, including gravity. Sorry, how to apply quantum mechanics to our entire universe, including gravity. That is a big question that's hard to answer. So let's try to simplify it. We can ask how to apply quantum mechanics to a universe with a positive cosmological constant, like ours. And that already comes with a whole host of confusions, which are pretty relevant to the topic of this workshop since it's related to boundaries, because we don't know how to do holography for de Sitter. We've done a lot of progress with ADS-CFT and similar dualities, but there are a lot of questions regarding how to have a holographic dual, if any exists, for de Sitter space, that is space-time with a positive cosmological constant. For example, there are a lot of proposals for de Sitter dualities. Some have a holographic dual that lives in the future or past horizon, so it's a Euclidean CFT. It's called de Sitter CFT. Others have an observer-dependent holographic dual that lives on the cosmological horizon. That would be or nearby. That's a holographic screen. Those are known as static patch holography, goes by those names. There are also proposals where the dual is not holographic in the sense that it is in the sense that it lives in a lower number of dimensions, but it doesn't live anywhere in particular. It doesn't reside in a space-time or a space that can be located anywhere in the de Sitter-Penrose diagram, such as ideas motivated by ensemble averages or double scale YK. So those are a lot of questions that I'm not going to dwell in this talk, but are going to underlie the motivation for my work. We can simplify this further to avoid these questions by working in two space-time dimensions. So this is going to be the focus of the talk. And the idea is that in 1+1 dimensions, we can apply the traditional canonical quantization methods, such as old-fashioned Dirac quantization and some modifications thereof, so that hopefully we can learn something in an agnostic way without having to explicitly work with proposed dualities, hopefully then learn something about what is a correct way to do quantum gravity in our universe, or at least for now, in small universes with a positive cosmological constant. So what's the simplest model of a 2D gravity with a positive cosmological constant? Well, that's known as Jackiw-Teitelboim gravity, JT gravity, in the de Sitter case with a positive cosmological constant. And this is its action. It's pretty much the simplest addition we can make to the Einstein-Hilbert action to make the model not trivial. The first term here is, as you see, the Einstein-Hilbert action, which in 2D is just a Gauss-Bonnet term. It's purely topological, so it doesn't give us much of interest. The second term that we add includes a dynamical degree of freedom, that's a scalar called phi, known as the dilaton, and it acts as a Lagrange multiplier to impose the equation of motion that r equals 2 in units where the de Sitter length is equal to 1. What are the benefits of this model that has two dynamical degrees of freedom? Well, the metric ones, which are more than one, and the dilaton. One is that it's 2D. And that means we can quantize it fully non-perturbatively because it boils down to just quantum mechanics as opposed to quantum field theory, and that evades the usual obstacles to quantization. And the second is that even though it's just a toy model in 2 dimensions, it has a positive cosmological constant like our universe, and therefore it has also closed universe solutions. And these two are some of the most confusing aspects of quantum gravity in cosmological spacetimes, including our universe. So we'll take it away with this model. And what I did last year with Daniel Harlow and Patrick Jefferson at MIT, well, Patrick is now at UMass Amherst, is to first find all the classical solutions to this theory, which is a prerequisite to quantization. Usually, when we find all the space of solutions, that makes a classical phase space, and it comes along with a structure called the symplectic form that we'll talk a bit more about later, that gives us Liouville brackets in the classical theory. And there are well-known quantization procedures that allow us to turn this into a Hilbert space along with canonical commutation relations and an inner product. So a prerequisite to quantization is finding all the classical solutions. But this took a long time. This was actually the most fun and interesting classical mechanics problem I've ever seen. So if you're not interested in de Sitter JT gravity, even though you should, at the very least, treat this as a fun classical mechanics seminar that is quite puzzling. In fact, it's so puzzling that it took people over 40 years, actually. There were even a few attempts before Hinot in 85 to find the classical solutions, but they kept missing some until last year we finally found all the classical solutions, all the ones found in the literature before, along with new ones that hadn't been discussed previously. So that's the introduction, and the outline of my talk will be, we'll first construct together the classical solutions, and I'll describe to you what the phase space looks like, and then you'll see why this was a hard problem and why it took over 40 years to solve. And then I'll comment on how to quantize the theory, which I complete in follow-up work that will come out soon. So there's a little ad for you. Any questions so far? Yeah. You can interrupt. Feel free. Oh. Oh, I will. Good. I'll highlight that. Yes, we'll construct them together, and then I'll highlight that. And if I forget to highlight it, please ask me again. Yes. And yeah, same question.
How do you know that they missed something?
Yes. No worries. I'll show you all the solutions, and then you'll see. All right. Any more questions? Good. Okay. So here's the JT gravity action again. And I've omitted the boundary terms, the Gibbons-Hawking-York boundary term as usual, because we're going to work with boundary conditions where there's no spatial boundary. The Cauchy slices we work with are going to be topologically circles, just periodic. Actually, that term will become important later in a subtlety that I'll mention. So even though it's a spacetime without boundaries, the boundary terms are important and will lead to confusion if you omit them. For now, you don't have to worry, but we'll come back to that. It's a little preview. So the equations of motion from this action are these two. The first one we saw is imposed by the dilaton as a Lagrange multiplier. The second set of equations come from the dynamical metric. And a convenient fact is that the first equation doesn't include the dilaton. So we can solve for all the geometries and then ask what dilaton profiles, there's a name for dilaton solutions, live in those spacetimes. And this problem is really restricted because in 2D gravity, there is only one local solution for the metric up to diffeomorphism. I'll write it in this form in this talk. You might be more familiar with this other choice of coordinates, but these are the coordinates for a global de Sitter. So locally, all the spacetimes look like this. So different solutions can at most differ by their global structure. Therefore, we're going to follow the following approach to constructing the solutions. We were going to start with the universal cover, which is unique, the universal cover of this metric. This is the same metric I showed you before, where the tau coordinate goes to minus pi over 2 to plus pi over 2. That makes it geodesically complete. And the spatial coordinate, which I call sigma, runs along the entire real line. Of course, this doesn't have the boundary conditions we asked for. This doesn't have closed closed Cauchy slices. But what we will do is, from this universal cover, take quotients of it in order to give the spacetime the topology of a cylinder. That's going to be the idea for the rest of this section. For example, here's a familiar solution we can construct in this way. If we quotient by a translation by 2 pi along the sigma direction, we obtain the familiar de Sitter hyperboloid. And this is the only solution that can be embedded in our 1,2 3D Minkowski. In the following way, where the metric we wrote earlier is the induced metric on this submanifold of Minkowski. And here's an explicit parametrization of the coordinates. This might be familiar if you studied de Sitter before. It's often a starting place. But it is not the only solution. It's just one in a whole phase space of solutions. More generally, what we can do is quotient this infinite strip, which is the name I'll give informally to the universal cover henceforth. We can quotient by any isometry of this universal cover, of this infinite strip. Quotienting by an isometry ensures that the metric remains smooth after taking this quotient. So these are the possible quotients we can take of it. So we need to understand the isometries of this spacetime. And then for any element of the isometry group, we're going to identify every point in the infinite strip with its image under that isometry, under the square of the isometry, cube of the isometry. That's all the powers. The isometry group of this infinite strip is the universal cover of the Lorentz group. Specifically, I'll pick just the connected component. I'll say more in just a second. And as I said, just to be clear, what formally we're doing is quotienting the infinite strip by the abelian subgroup generated by each element in the isometry group. Because the abelian subgroup contains all the powers of some isometry Q, so we're identifying X with Q acting on X, with Q inverse acting on X, etc. Any questions so far? All right. Yeah.
Are you going to make this non-orientable or?
Yes, so I will actually try to keep the orientation of spacetime and not quotient with flips in time reversal or parity. Moreover, then later when I gauge, I will also not include parity and time reversal in the gauge group. There are discussions about whether to do this, but to avoid some pathologies, I will stick with this parametrization. And that's exactly the reason, you got ahead of the game, why I'm keeping just the connected component of the Lorentz group, the connected to the identity. So I'm not including time reversal or parity. And that's a choice that you might try to look at. There's a discussion last couple of years from Harlow and Numasawa about gauge, in particular the gauging part of time reversal or parity. That's quite interesting if you're curious about that. Good. So here's a bit of intuition for why the isometry group is this universal cover of the Lorentz group, the connect component to the identity. So before we constructed the Zeta hyperboloid, and actually that's a very special submanifold of Minkowski space because it inherits all the isometries from 3D Minkowski. And yeah, there we go. So the isometry group of the hyperboloid is the connected component to the identity of the Lorentz group. The infinite strip is the universal cover of this space. So its isometry group is the universal cover of the connected component of the Lorentz group, which you might also call PSL2R, whatever. I'll call it G henceforth, so I don't have to say those words all the time. And this group results from simply a central extension of G, where we're including 2 pi translations or 2 pi n translations for any integer n in the group. Those 2 pi translations along the sigma direction were the identity element in this group, since they simply rotated you around the hyperboloid in a 360 degrees. But in the infinite strip, a 2 pi translation in the sigma direction is non-trivial, and therefore those become elements of the universal cover. And they commute with all the other elements, so they're the center of the group, thus the name central extension. So this is just the Lorentz group together with 2 pi n translations along the spatial direction sigma for any integer n. So now we have, oh yes. Yeah, so I'm just, it will come up later. I've just decided to call T a 2 pi translation, and so T to the n would be a translation by a quantity 2 pi n for any integer n. I wait to see this in Minkowski only, or say? Kind of, yes. So it's actually quite analogous to the usual picture of universal covers of groups, since in Minkowski, this is embedded there. The rotations here, the group of rotations, becomes non-compact. So even though the Lorentz group has a topology of like circle cross at R2, the universal cover has topology of R3 where we've unwrapped that circle. Kind of, well, yeah, so the spin group would be the double cover, and this is just the infinite cover. Did I answer your question? Good, but we're not done yet, because not all isometries are distinct. Some of them are related by gauge transformations. In particular, if we do a little algebra, we can see what these gauge transformations are. So we labeled a spacetime from the quotient that we take of the infinite strip. So we label a spacetime by Q, where Q is an element of G tilde, the isometry group. But we could do a gauge transformation by any other isometry. That would be this H. I'm acting on all points in spacetime. then do a bit of algebra and insert the identity, and simply then relabel the point we're looking at, since every point gets identified under the isometry. So look at h acting on x instead of x, and we see that if we take an isometry and look at a different one that's conjugated by any other element of the gauge group, they label the same spacetime. So in particular, the adjoint action of G tilde in itself, that's action by conjugation, is a gauge symmetry. So that would be this quotient we take here. And moreover, Q and Q inverse also generate the same abelian subgroup. Telling you I'm identifying every point X with its image under Q means I'm also identifying every point with its image under Q inverse. So both Q inverse and Q generate the same subgroup, and therefore they are the same isometry. And also conjugation captures the diffeomorphisms. Therefore, the actual group of isometries is G tilde modded out by the gauge transformations, which are the adjoint action and the inverse. Question there. Yes, it's diffeomorphisms. It's just here that because we've already restricted to isometries Q, so we keep in a choice of gauge for the metric, then if we acted by any more general diff, that would take us away from G tilde. So this is the part of the diff group that acts on the group of isometries. So these are all the gauge transformations. Any more questions? Good. So that was a lot of math, quite abstract. And I personally like to look at space-time diagrams. So let's get a feel for what these solutions look like. Here I've drawn these space-time diagrams, the infinite strips, again with tau in the vertical direction, sigma in the horizontal one. And I've drawn for you distinct isometries in G tilde by their Killing vector fields. The first one looks like a translation along the sigma direction, the bottom one like a boost, and the middle one is a shear or null rotation that's a special combination of a boost and a translation, or rotation in the case of just G. And some convenient gauges, so the diagrams look pretty. Then an isometry, we view quotient by an isometry corresponding to these space-time diagrams in these Killing vector fields. What we're doing is identifying the black dashed line here, or any other point, but I'm looking at this black dashed line as a reference, with the colored one, which is its image under an isometry. In particular, just to be very explicit, each isometry Q acts on tau and sigma in the following way via these matrices, where you can then see explicitly that the top one looks like a rotation, the bottom one like a boost, and the middle one we're not used to seeing as often, but that would be this other set of null rotations. But of course, I'm being a little cheeky here because G tilde, unfortunately, doesn't have a matrix representation. However, we can get around this by a clever parametrization of this group, because what we also need to include to get to G tilde are the translations by 2 pi n. So we can identify the black dashed line with its image under this, well, let's look here, this boost, or also its image under the boost and a 2 pi n translation, etc. So more generally, we can represent an element in G tilde by an element in G, which does have a matrix representation, along with an integer n that labels a number of 2 pi translations. We formalize this a bit more in the paper, just to be very clear of how the parameterization works. But this is in spirit what's happening. Moreover, actually, there exists a bijection between the Lie algebra of G and G itself, as long as we restrict the Lie algebra to a certain set of elements, which, again, I'll discuss in detail in the paper. It won't be super relevant right now. But the idea is that because we're working with just a connected component of the Lorentz group, we can then parameterize uniquely every element of G by a set of Lie algebra charges. It's 3 Lie algebra charges. In particular, for the first one in this convenient gauge, that would just be a translation by an amount A, and the second one by an amount B, and the third one by an amount C, which is the amount we move along these integral curves. And these are the Lie algebra charges, as these matrices are the generators of G. So for more general transformation that's not in one of these nice gauges, we can then parameterize, or just put coordinates on G tilde, the isometry group, where we label every isometry by a vector, a 3-vector Q of the algebra charges, and an integer n. For each of these, the vector Q is kind of intuitive because for these distinct families of isometries, Q has a different signature. For the first one, it's time-like, for the second one, it's null, and for the third one, it's space-like. So these different Q will generate different isometries that look like these up to diffeomorphisms. Any questions so far? That is very right. That is kind of an issue, and I will come back to that. I have a slide for that. It's kind of a fun quotient. Okay. And moreover, actually, if you remember the gauge group that we discussed earlier, conjugation is a diffeomorphism. It's pure gauge. And conjugation acts on the Lie algebra by just the Lorentz group rotating or boosting this vector Q. So actually, the only continuous gauge invariant parameter telling you the geometry is the norm of this vector Q. There's also discrete parameters that are related to its signature, but the only continuous diff invariant parameter that we identify just based on this geometric approach is the norm of Q. Now, if everyone's happy with the geometries, we can go back to the other equation of motion, the one for the dilaton, and simply ask what dilaton solutions we have on these possible geometries. So this is the equation of motion that we obtained for the dilaton, and this is the form that the most general solution takes. And I want to highlight important fact that it's parameterized by 3 parameters, not fields. Again, this is what made us work with, in the quantum theory, this will be quantum mechanics as opposed to a field theory. So the most general dilaton solution is parameterized by 3 numbers, which I've conveniently labeled V0, V1, and V2 to make you think of a vector or a form. But phi must respect the global structure of the underlying geometries. In particular, for phi to wrap around smoothly in the cylindrical spacetime, it must respect the asymmetry that we quotiented by. Otherwise, it would not wrap around smoothly. This turns out to translate to the condition that V as a vector must be proportional to the vector Q that we found earlier. So then again, the only continuous diff invariant parameter, gauge invariant parameter, labeling the dilaton solutions is the norm of this vector V. Any questions or that? Was that a little fast? Are people happy?
Will you say later what did they miss in the previous solutions?
Ah, good. Okay. I'll tell you right now what the dilaton is, and then I'll tell you exactly what people missed. Perfect. Thank you. Okay, first one comment. Obviously, in 2 dimensions, we only have one spatial dimension, so there's no notion of area or volume. So this theory is really, really simple. However, we often interpret in JT gravity the dilaton to be a proxy for a notion of area or volume. This is motivated by how JT gravity can be obtained as a dimensional reduction of a 4D theory, in particular near-extremal black hole limits. ADS-JT with a negative cosmological constant, just as a flip in the sign of the action, can be obtained as a dimensional reduction of the near-extremal Reisner-Nordstrom, whereas de Sitter-JT can be obtained as the near-extremal limit of de Sitter-Schwarzschild. Near-extremal, it's called the Navier limit, is the limit where the black hole horizon approaches the same size as the cosmological horizon. And in those cases, the dilaton represents the area of spheres in these spherically symmetric spacetimes. In particular, the regions where the dilaton goes to plus infinity represent expanding, inflating regions, which I've labeled here as a de Sitter boundary, whereas the parts where a spacetime where the dilaton goes to minus infinity represent curvature singularities in the higher dimensional theories. I will not try to make conclusions about 4D gravity from JT, since those are just perturbative. They are near horizon limits of them. I'm taking 2D gravity to be a toy model for gravity, good in itself. But I will make a connection I will just be inspired by the 4D theories to interpret the dilaton as a volume, just so we can do some physics and have some physical intuition for what these spacetimes represent in these, after all, toy model. So these three types of solutions correspond to expanding or crunching spacetimes in the first two, where the dilaton's going from minus infinity to plus infinity, or the other way around. And in the bottom one, we have n black holes, labeled by that integer n, interspersed with de Sitter regions, with inflating regions. Now, okay, the solutions that people missed before include, there's been a lack of discussion about these solutions where Q is null altogether, which are important in that they connect continuously the top and the bottom solutions, as we'll discuss a bit when we see the phase space. And then in the bottom one, in the context of de Sitter JT, people had talked about the black hole solutions before, although usually those people then had forgotten about the other solutions in the same paper, but they hadn't considered this boost that we can also take. So they had only considered solutions where this gets identified by 2-pi translation, but not by also a boost. And I wanted to say one more thing. Yes, when people try to characterize the entire phase space in a group theoretic way, like we did, we looked at configuration space as this detailed Mott-Legage transformations. The only people that had tried, as far as I know, to write the configuration space in that manner had not taken the universal cover, had only worked with cylinders at most of length 2-pi. Both for the geometry and then for the corresponding dilaton.
New solution. Yes.
For 2D, at least, yeah. So ADS is a lot simpler. And it actually looks like just take these spacetime diagrams and rotate them 90 degrees. And it's simpler because in ADS, we work with boundary conditions where the dilaton's going to plus infinity on the boundaries. We don't want a time-like singularity. And so the only case where we can have that is you take this bottom diagram, rotate it 90 degrees. That's why we only talk about black holes in the case of ADS JT, or then quotients thereof. And moreover, all of these business with the infinite strip, which is giving us this richness in how we identify whether we have a boost or not, disappears in ADS because we don't want closed time-like curves. So we're not interested in quotienting in the time-like direction. And in particular, we just cut off the spacetimes at the Cauchy horizons, bottom and top. So the phase space is a lot simpler. It is still two-dimensional, in the sense that this one's two-dimensional because we have two continuous different variant parameters, and we'll justify that more later when we calculate the symplectic form. And in ADS, you also have just two, but the phase space looks like just a plane topologically, whereas here the phase space will be a lot more complicated. Does that answer your question? Asymmetry, do these have like an isometry group each? The remaining isometry, the only isometry that survives from the original G tilde in these quotients is the isometry that we quotiented by. So you can see geometrically what like the isometry parameterized about those horizontal lines for the integral curves in the top one are not an asymmetry anymore if we quotient including a boost, like for example in the bottom one. So the isometry group generically reduces from 3 dimensions to 1 after taking these quotients. Any more questions? Yes.
This construction is inherently Lorentzian.
That's right, yes.
Only have the bottom solution? Is that the idea, or?
So actually, you would only have the top ones, and a very special one for that matter. Yeah, so that's a good point. Just I wanted to stress that I'm doing everything in a Lorentzian way. Path integrals are confusing. In fact, that's yet another reason to try to study this, hopefully to learn something about gravitational path integrals, dualities, etc. But all my work's going to be, it's Lorentzian here. If we look at just purely Euclidean solutions, the only positive curvature solution is the sphere with de Sitter radius. And the only geodesics there, the great circles there, can only be continued to the top solution under quotient by 2 pi. So exactly the de Sitter hyperboloid. Any other Cauchy slice in these geometries is not going to continue to a smooth Euclidean solution.
Okay. My second question, you constructed these solutions, but you're claiming that you have some sort of uniqueness, that these are the only ones.
Yes.
But I have not seen that.
That's true. Very good catch. Let me also stress before answering that bit that the bottom family of solutions is such that there is no smooth Cauchy slice. And there is let me say clear. Sorry, there is no geodesic Cauchy slice here, or even a Cauchy slice that has constant extrinsic curvature. That's what makes it so that any smooth Cauchy slice you pick cannot be continued to a purely Euclidean geometry. And in fact, also a reason why people who've attempted quantization of de Sitter JT in the past usually, I'll get back to your other question in a second. People have looked at quantization of de Sitter in the past have done so in a convenient gauge fixing where they, for example, fix the extrinsic curvature to be constant or the scale factor to be constant in a mini superspace type of approaches. And those missed these solutions. So that's why the quantization of de Sitter JT hasn't been completed, precisely by that issue with the how to pick nice Cauchy slices here, which is closely tied to Euclidean continuations. Yeah, so I wasn't going to dwell in this uniqueness. Of course, I've shown you how I found more of the solutions than in the literature, but are these all the solutions? The intuition behind that, although I have not formalized it deeply mathematically, is that if you take the infinite strip, which of course is unique, so I'm happy with the construction where we're taking quotients. Question is, are these all the quotients we can take? Once you've quotiented by one element Q, if you quotient by an element Q that commutes with it in the group, then it's just a similar type of Q. It will just be a Q that is where the vector capital Q was parallel to it. So if we quotiented by one boost, then the only one that would commute with it is another boost. And now this asks two questions. Does this give you a new thing? And also, is there a possible quotient by something that didn't commute with the original isometry? The first question, if we quotient by another boost and these two boosts have a rational quotient, then that's equivalent to just a boost by sort of the minimum common divisor, the maximum common divisor. If you quotient by a boost that has an irrational ratio with the original one, then those will just end up reducing to a 2 pi quotient, which we also include here. If you try to quotient by another, you take a first quotient and then try to quotient again by something that didn't commute with the original Q, then you're not quotienting by an isometry of that spacetime, and therefore the resulting metric is not going to be smooth and Lorentzian everywhere. Yeah.
That you have to quotient by an element of the group to get something smooth. Is that clear? I know that it's true that if you take by an element of the group, you quotient by an element of the group, you will get something smooth.
Yeah.
But can you try to quotient by something else that is not an element of the group and yet get something smooth?
I wouldn't think so, because locally the metric looks the same everywhere, and so if I transform that by an isometry, then the metric is not going to wrap around smoothly, right? Like if I just look locally at the change of coordinates at a point, if I just transform the metric by something that's not an isometry, it's going to look different as I wrap around the cylinder, no?
It's not clear to me that
Okay. There's also there's certainly other like groups people have studied, other subgroups of G tilde, such as these like Fuchsian groups. And the issue with those, and these are not all the groups, but just like that gives me some intuition, in that those are not abelian generated by a single element. But if we try to quotient by those, then what we generally obtain are handles on the spacetime, and that fails to be Lorentzian, at least at 2 points. So that's the type of pathology that happens. You can't be smooth everywhere or Lorentzian everywhere if you try to quotient by those groups. Yeah, I'd be happy to talk more if you have some intuition for what types of quotients by non-abelian subgroups might give a smooth geometry if you have any minor thoughts. Yes, I'm required to. And that's very restrictive. Yeah. Yes. geodesically complete Cauchy slices with a circle topology, purely Lorentzian, and just a single, yeah, the circle topology is one connected component. Yes. Yes, that's right. And in fact, now we're about to talk about the solutions with n equals 0, where we're quotienting by a boost, and we'll come back to global hyperbolicity imminently. Any more questions? Sorry, I feel like I'm ignoring this side of the room. All right. Okay, so now onto this confusing set of solutions. There are two types of pathological, or at least confusing quotients that result from quotienting with little n equal to 0. They come from both this type of solutions and the bottom ones. Let's look at these ones first, and then we can generalize. If we quotient by Q space-like and little n equal to 0, we obtain this interesting geometry that is a collection of an infinite sets of double cones that meet at a conical singularity, connected by regions that where every point is part of a closed time-like curve. They're therefore totally vicious would be the name. Because when we take in the quotient, what we're doing is identifying this vertical line with its image under a boost, and also this one with this one, every point with its image under the boost. And therefore, in this region, every point is identified with a point in its future, and that's what causes all these closed time-like curves. This quotient is problematic for two reasons. One, the obvious one, is the totally vicious regions. We don't usually like to have closed time-like curves. Yes, we don't like to have closed time-like curves unless there's an a priori reason to throw them out. I wouldn't personally, but that is certainly a puzzling aspect that challenges global hyperbolicity. And moreover, there's another subtle problem with these, and it's that it contains 4 distinct sets of initial data, solutions that have a conical singularity in the past or in the future, and where the dilaton is positive or negative. This is problematic because in our phase space, these are represented by only 2 points in the phase space. And usually the phase space, every point in phase space should uniquely capture one solution via one set of initial data. The reason this happens is this is one quotient Q, and then putting the dilaton on top of that is going to give us 2 points in the full phase space. This is puzzling, and in order to deal with it, we proposed a posteriori the following rule. There might be others, but this is one intuitively physical suggestion we make, which is we propose to view as physical only spacetimes resulting from these quotients that contain a de Sitter region in them. Since after all, we wanted this to be a theory of de Sitter, this is an a posteriori rule, which you may or may not agree with, but what it does is it both throws away half of the initial data, the ones where the dilaton is negative, because in those cones, there is no part, no de Sitter part, no part where the dilaton goes to plus infinity. And moreover, it also throws out the totally vicious regions, since they also don't have a de Sitter infinity in them. And this is kind of a posteriori way to interpret how there are only 2 points in phase space to label this madness with 4 sets of initial data and totally vicious regions in them. Any questions and comments? Well, yes, well, that was kind of I wasn't going to insist on global hyperbolicity in the beginning. It was kind of more, in the end, I'll end up classifying things that are only globally hyperbolic. That's another way you could say. You could get rid of the totally vicious parts by saying I want to exclude the regions that are not totally hyperbolic. Fair, great. Yeah, they are trivially not geodesically complete. That's one option. I'm not going to ask for just geodesic completeness, because the double cones are generated by two different sets of initial data, and at the singularity, the conical singularity, the geodesics get cut off. So I'm actually not insisting in geodesic completeness. Yes, Lorentzian locally 2D de Sitter with a de Sitter infinity region in them. And Cauchy slices circles. In those cases, I think the impediment is that they're not going to be Lorentzian everywhere.
Remove the points. Remove the points where it's stopping Lorentzian, and then you have now a manifold, a space-time that has a singularity, that has an endpoint.
That's confusing though, right? Because I think in those cases, if you take those sorts of quotients, the places where you fail to be Lorentzian are 2 points, in the sense that you're including handles. And so these are 2 points in the middle of the bulk of the spacetime. If I remove them, then I have to remove part of the future of these points. Well, actually, no, like here in this conical singularities. Yeah, okay, I grant you that. Let me say I am only allowing to remove points that are either in the future or in the past, but not in the middle of the bulk. That would be, I guess, a characterization of the remaining solutions that I'm describing here, since I'm allowing for these conical singularities in the double cones. I think that would be a sentence I'm happy with characterizing these solutions. This problem also arises for the quotients where Q was null in the previous picture. In those, they're slightly less problematic because the singularity is off to conformal infinity, so it's already not part of the spacetime. But they also have the issue with twice as many sets of initial data for the points that label them in phase space. And this rule also takes care of those, as it throws half of the sets of initial data because the dilaton is everywhere negative. Good. Any more questions or complaints? Well, that's I'm thinking more generally as just specify for me a dilaton and a dilaton field and an induced metric. Yes, or in this parameterization, you can ask for that, or equivalently specify the Q0, Q1, and Q2, which I haven't told you what that looks like on a Cauchy slice. It corresponds to an integral observable. You have to integrate along the entire slice, since it has to capture the global topology. And actually, it might be worth saying some physics words, if you allow me to just go back a little. The norm of V, just to give some intuition for what the norm of V and the norm of Q are in these spacetimes. The norm of Q in the different families of solutions corresponds to different words to describe them. In the first one, the norm of Q is the proper length of the usually only, or at least any geodesic that wraps around the cylinder smoothly, of course, so it's geodesic everywhere. In the bottom one, the norm of Q corresponds to a boost that you inevitably pick up if you try to parallel transport a vector around a geodesic all the way around the cylinder. It inevitably gets boosted by an amount that's the norm of Q. This type of boost has also been described before in 4D for periodic solutions of de Sitter-Schwarzschild. And then the middle one is a little more confusing since the norm of Q is null. In particular, what happens is that this boost that we quotient by at the top actually can be absorbed into the dilaton and vice versa. So they become just a measure zero, just a line within the two-dimensional phase space. We'll see them in a second. Yes, and the norm of V in the bottom set of solutions corresponds to the value of the dilaton at the in these points at the bifurcate horizon of the black holes. And in the top one corresponds to the rate of change of the dilaton on this geodesic that wraps around smoothly on the tau equals 0 slice, which is generically the only geodesic that wraps around. And again, in the middle one, it can be absorbed into the boost and vice versa. So there's not such a clear interpretation. Any questions about that? Or about anything? Say again, sorry?
The middle one looks like extremely Schwarzschild.
Yes, actually, with the on the Poincare patches. Yeah, Yeah. Oh, nice. I haven't actually ever like derived that Penrose diagram, so I'm curious. Okay. So I've told you this a posteriori rule, and now we're ready to look at the phase space. How am I doing on time? Is there a clock in here? Oh, beautiful. Okay. Good. So we're ahead of schedule. So if you have questions, please by all means ask. Now we're ready to look at the phase space and understand why this problem is being so confusing. The phase space is the set of physical solutions where every point in phase space labels one solution through also or equivalently one set of initial data. So there's a set of solutions modded out by the gauge transformations. This is my best attempt at drawing the phase space. It's very weird. It's hard to draw. But there is a rigorous mathematical description of it. In this picture, along these lines, you can see there's this blue line and these like yellow teeth poking out of it. Is the directions where the norm of Q is increasing, and vertically is the regions where the norm of V is increasing, at the top where the relative sign between Q and V is positive, bottom negative. This phase space, every point labels one solution, and it extends infinitely throughout the top and on the sides, so it is an infinite collection of half planes that intersect. And this problem was so confusing because this phase space is not a manifold, since at the points of intersection it fails to look locally like R2. And moreover, it's not even Hausdorff in the sense that there are some solutions that sit right on top of each other in the sense that all their neighborhoods intersect no matter how small I pick them. I'll tell you exactly which ones. And usually in a lot of treatments of phase space in classical mechanics, phase space is assumed to be a manifold, or at the very least, it's assumed to be Hausdorff. It need not be either. So at least if you're going to take away something from this talk, keep that in mind if you're ever doing classical mechanics. But that is one of the confusing aspects that made this problem hard to solve. Let me tell you what these different points in the phase space look like. So before we looked at the different types of solutions based on Q, in this blue half plane that extends infinitely that way, every point labels one of the solutions where Q is time-like. So they're expanding or quenching. The yellow half planes label the solutions where Q is space-like, and there's one plane for every integer n. So this first plane labels the two cones with a positive or cones with the conical singularity in the feature in the past, above or below this yellow line. And then in the rest of the planes, n labels a number of black holes in those leaves. And then at the points of intersection, we have the solutions where Q is null or Q is identically 0, which corresponds to identifications by just 2 pi n translations and no boost on top of that. These are the solutions that sit right on top of each other and break Hausdorffness. That's why I've tried to draw them with this dashed green and black lines to indicate that they're sitting right on top of each other. So this was hard to draw for those reasons. I can't properly draw a non-Hausdorff space on the board. But there will be a group theoretic description of this phase space that I'll show you in a little bit that is much nicer to write down than this picture I drew here in my best of attempts. Can you say again?
Why the phase space is unnecessary to be the method? Usually we consider the symplectic method, right?
Yes, well, this will have a symplectic structure, at least on each of the parts that don't break the non-Hausdorffness. The non-Hausdorffness and non-manifold will be an issue for quantization, mainly non-Hausdorffness, and I'll explain in a minute. Well, in a minute, at the end when I comment on quantization. So see, that will be an obstacle toward the traditional quantization, but we can avoid it in a way that I'll describe. Does that answer your question?
Yes.
For now.
Did you compare other quantization?
Other different types of quantization, you say? That's an interesting aspect that I'll comment on at the end. And if I don't comment on it, please remind me. Yeah. Like in math, often examples are like kind of silly. The canonical example for a non-Hausdorff space is the real line with two origins, in the sense that you're putting two origins that are like, infinitely close, and so that every other their neighborhoods intersect. Okay, this might help or not, but there is actually a way to see how this non-Hausdorffness comes up in this particular problem, and is that I mentioned that you can think of the adjoint action of the gauge group as boosting or rotating this vector Q by Lorentz transformations acting on the vector capital Q. So if you think of the vectors that live on the light cone, I can do boosts, which are just pure gauge, to bring them arbitrarily close to the origin. And the origin itself is a different such solution, it's a solution with Q equals identically 0. That's a different orbit. It gets left invariant by Lorentz transformations. So the future light cone and the past light cone in this parametrization in terms of vector Q end up sitting right on top of the origin, and that's what breaks non-Hausdorffness. Any more questions? All right. So now, remember, we've looked at all the solutions, all the points in the phase space, but that's not the entire phase space. We need the symplectic structure. The symplectic form is a closed, non-degenerate 2 form on the space of solutions. And to give you some intuition, this form is important because we can use it formally to turn any scalar function into a vector field whose integral curves tell you how to evolve by evolution generated by the scalar function. For example, the Hamiltonian H. To see this clearly, for a particle in a potential, or a free particle, just a particle in general, the symplectic form looks like dp wedge dx, where p is the momentum, x is the position, and d means a variation, an exterior derivative in phase space. So then if we have some function h, we can vary h to obtain a form, and then act on it with the inverse of the symplectic form, which is invertible because we assume it's non-degenerate. We construct it to be non-degenerate. By contracting those two, we can turn the form dh into a vector, which is exactly the Liouville bracket that we calculate in quantum mechanics. So even if you haven't heard the word symplectic form before, or you haven't worked with it, secretly you all have, because you have calculated Liouville brackets in classical mechanics. And in particular, when the scalar function is taken to be the Hamiltonian of the theory, this is exactly the time evolution. So the symplectic form is essential, and we use it all the time to turn a scalar function h into time evolution, or any other type of evolution for any other function. And I'll go now into a bit of details of how you calculate the symplectic form. If you haven't seen it before, it might be a little fast, but the idea that I want to transmit to you is that this is a well-known procedure. There's a well-known prescription for how to calculate it. And that boundary terms in the action are important in this case. So say we have a theory defined by an action, and it has a Lagrangian L and a boundary term given by little l. A variation of the Lagrangian part gives you the equations of motion, along with possibly a total derivative. And we usually throw that out, but it's actually very important, and it's that total derivative that we need to use to calculate the symplectic form. More generally, the idea is that to get the equations of motion, the action is stationary when the equations of motion are satisfied, up to boundary terms in the future and the past. Those boundary terms, which are given by this theta, are exactly what we use now. Combining them with the boundary terms of the action gives us this other quantity c, and then we're using this theta and this c, so all these boundary terms, the future and past, to calculate the symplectic form. And the pre-symplectic form, which might not be invertible, corresponds to an integral of these quantities over a Cauchy slice, and then a phase space variation. So the takeaway is that boundary terms in the action are important when you're calculating symplectic forms, and this will come back to bite us later. That the action is stationary when the equations of motion are satisfied up to boundary terms of future and the past. This is why we don't impose boundary conditions in the future and the past when we're defining theories. And that to calculate the symplectic form, we do an integral over a Cauchy slice. Then the last step is just quotienting by the zero modes of this form, this pre-symplectic form. And therefore that takes us from the unreduced phase space, which is a space that's too large, and gauges the gauge and quotients by the gauge transformations. The zero modes of the symplectic form, the directions in the unreduced phase space where it's zero, correspond to the continuous gauge transformations. So if you missed some gauge transformations when you were trying to analyze the solutions in your theory, it's not a problem, because if you rigorously calculate the symplectic form, it's going to tell you directly what are the continuous gauge transformations. So it's a pretty powerful object.
Sorry, I missed the point. Which is your boundary? Where do you put the boundary conditions?
Yes, my only boundary conditions in defining the theory here are spatial, saying that there's no spatial boundary, specifically that the Cauchy slices have the topology of a circle. Yeah. No, I'm just going to remove them, I was thinking. All right, any other questions? Good, yes. Like here, well, I'm using M to just label the entire space-time manifold, and dm is the boundary, either future or space-like, yeah, the entire boundary of the manifold. It depends. It requires more care, but there is, if you just pick one of the points where it's non-Hausdorff, you can still pick a neighborhood as long as it's only going in two of the directions. Like if you're in a null solution, you can look at the nearby time-like and space-like solutions that it connects to, but it's a little trickier to calculate, certainly. Does that make sense?
Okay. Not sure how you define the these big series derivatives for non-Hausdorff.
You can look at the tangent space or cotangent space later, we'll see at each point where it's not a manifold or not Hausdorff look like an intersection of half-lines if you're trying to generalize the notion of tangent space for a non-manifold. And there are different tangent spaces that also sit right on top of each other for each of the points where it's non-Hausdorff. So in a sense, in the line with two origins, you could think of the tangent space at either of the origins as also the line, but they're different tangent spaces at each of the 2 points where it's non-Hausdorff. So it requires care, but if you localize into just a single solution, then there's still a notion of tangent space and deforming the solution. Say again, sorry?
Is one of these origins next to the other? It's not a vector going, there's no direction.
That's right, yes, there's no direction connecting them. You would have to sort of go away to another solution and come back. In the case, for an intuition, if this helps, if you start with a solution with Q was null, so one of these diagrams I drew earlier, you can deform it a little bit to get this, I don't know if this is going to help. The curve where the dilaton was equal to 0, I'm too far in the slides for a picture. In the null solutions, looked like this zigzag. It's like the boundary of the Poincaré patch. You can deform it a little bit so it is detached from the boundaries, and that gives you a time-like solution in an inconvenient gauge where the lines of curves of constant dilaton are not flat. Or you can, and so you can go that way. So that was going from a point where Q is null into the blue plane. And then you can do gauge transformation to straighten that out. And then you can move the translation that you had quotiented by to get that time-like solution to a 2 pi quotient. And that brings you back to the line where things were non-Hausdorff, but now with Q equal to 0 identically. If that didn't help, I have more pictures that I can show later, because that was very physically hand-wavy. But the idea is that you can deform, you would have to like go into the yellow plane or the blue plane and then come back continuously if you want to hit a point that sat right on top of your original point. Sorry if that was a little much. Okay, now back to the symplectic form, unless there are any more questions. In the CIDR-JT, the calculation of the symplectic form is quite subtle, because if you try to follow this well-known, well-studied approach that I just described to you earlier in the previous slides, you get nonsense. These are the two, and these are the second set of challenges that, in addition to the non-Hausdorff, non-manifold phase space, made this problem hard to solve. There are two particular challenges to calculating the symplectic form in de Sitter. One is that the approach I just described for you relies on the ranges of the spacetime coordinates, not depending on what point in phase space you're at, on what solution you're trying to study. But here, of course, that is not the case. In the case of the solutions where Q is time-like, the range of sigma is exactly dependent on the space-time point. That is exactly the norm of Q, the observable we're interested in. So the ranges of the coordinates that we're working with do depend on the point in phase space. Moreover, if you try to calculate this theta object that I outlined for you earlier, that coming from that boundary term from the variation of the Lagrangian, it happens to look like a total spatial derivative in such a way that the integrand of this Cauchy slice integral that gives you the pre-symplectic form is an integral over a total derivative. So at least naively, if we apply Stokes, we get a vanishing pre-symplectic form, because it's an integral of a total derivative over a closed manifold. That's puzzling because it seems to say that every direction in the unreduced phase space is pure gauge, and therefore all the solutions are equivalent to each other by diffeomorphisms. But this is kind of counterintuitive. This can't be right because we studied the solutions earlier, and we couldn't find gauge transformations that would transform from one to another. So in fact, this is just wrong. And here are the resolutions that we showed for these two problems. The first one is to change the coordinates we're working with. We introduce a diffeomorphism that acts like the identity on one point of, say, this universal tiling as one of the spacetime that we quotient. It acts trivially on the left, but it straightens out the boundary on the right. So basically, at the cost of not working with this nice convenient form of the metric anymore in this nice gauge, we can work with coordinates that are independent of the point in phase space, at least locally in a patch around a point I'm studying. So this involves introducing this diffeomorphism, which I'm calling C, which smoothly transitions from being the identity on the left here to undoing the isometry on the right. For the second point, it actually turns out that this total derivative that we need to integrate over the Cauchy slice is the total exterior derivative in spacetime. That's the regular d is exterior derivative in spacetime, the curvy d in phase space. You don't have to worry too much about it, but just to clarify the notation. That quantity QC is the Noether charge associated to this diffeomorphism C. And in particular, because it acts like the identity on the left boundary of our integration domain and non-trivially on the other side, this dq is locally exact, but not globally. So that in particular, you see the final result is the value of q up to that variation we take in the end. It's the value of the Noether charge on the right minus the value of another charge on the left. On the left, C was trivial, so that Noether charge vanishes. But on the rightmost point, on the image of Q, it does not. So in other words, again, this boils down to the fact that this is locally but not globally exact. Or in other words, as we're doing the integral around the Cauchy slice, we're picking up a monodromy given by the Noether charge of this diffeomorphism C. So there are different words, they might help differently different people, but hopefully at least one of those sets of explanations rings a bell. So this introduction of this Xi is a way to solve both problems, to make the well-known procedure to calculate the symplectic form actually work. Any questions, comments, concerns? So that was a bit technical, but the takeaway is that if you try to naively calculate the symplectic form, you're going to run into a lot of trouble. You have to be careful, and in particular, even though the space-time has no boundaries, our Cauchy slices are circles, the most helpful way, and the only way to actually apply the procedure that's already well established, is to consider an integral in a sort of fundamental domain where the Cauchy slice, we forget that it's a circle, and we actually take into account two boundaries of this fundamental domain, the one on the left and the one on the right. And to calculate the symplectic form, we need to make sure we're keeping the boundary terms in the action, the Gibbons-Hawking-York terms. So these are all the ways in which not having a boundary is confusing, and we actually can avoid the confusion by thinking in terms of a fake boundary of when doing the calculation of the symplectic form. Yeah, is this when you're doing the calculating symplectic form on this slice, you can think of it as doing just the integral over this fundamental domain of the infinite strip and forgetting that you're quotienting it. And then you're sort of creating these fake spatial boundaries, these. Say again, sorry? The action, the way I wrote it earlier, technically I could have written the boundary terms. I just submitted them because I was working on a closed universe. So if you're trying to calculate the action on the entire manifold, it seems like they would vanish spatially. But they're important, mainly even in the calculation of the symplectic form, because you're varying things even on fake boundaries, but for things to be consistent, you need to take into account that the action did originally have some boundary terms, which we omitted writing, but they are there if you were ever doing calculations with a boundary. If we had looked at the theory, for example, with a different topology, instead of Cauchy slices that are circles, we had looked at the infinite strip and just put boundaries there, then the action, we would have had to be careful about the Gibbons-Hawking-York boundary terms there. That's exactly the picture that's happening here. Hope that was helpful. Any more questions?
Just the Gibbons-Hawking.
It is for the dilaton. It's like you insert also like the constant phi naught plus phi. Yes. 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 Yeah. Fine. There isn't, in the sense that, well, I mean, maybe there's a way to think about it in those terms. I haven't, in the sense that the spacetime lives just on the cylinder, not inside. But there might be a way to think of it as a flux going through this non-spacetime. I haven't thought of it in those terms, but I think there might be an interpretation in that way. That would be interesting. Okay. Yes, good. Okay, so it's the recap. The symplectic form is actually, the presymplectic form is actually non-zero. Now I'll spare you the details of the explicit calculation in the de Sitter JT. It's a little gory, but it's fully gravitational. It makes sense. And the upshot is that the symplectic form ends up being dv wedge dq, where v and q I'm referring to the norms of these two vectors. And therefore, this confirms that these are the two continuous gauge invariant parameters. What we found in our treatment earlier was correct. And in fact, the norm of q and the norm of v are the canonically conjugate variables, since they appear in the symplectic form in this form. It's like x and p did for the particle in a line. up to subtleties regarding science in frontier, which I don't dwell in, but are fully understood and we explain in detail in our paper. So that's a result for the symplectic form. And then finally, just to wrap up, I said earlier that even though the drawing of the phase space was weird, there was a nice mathematical structure to it. In particular, this phase space can be written as a cotangent bundle, where the base of the cotangent bundle is the space of geometric configurations we found earlier, G tilde mod the gauge transformations, and where we've also removed the identity element of G tilde, since it just corresponds to a quotient by nothing, so it cannot give you a topology of a circle. It's hard to interpret. If you quotient by nothing, you're either identifying a point with itself, so it's so it corresponds to a no volume solution, or you're not doing any quotient, and so you have the infinite strip. Either way, it's not part of our theory based on our boundary conditions. So we remove the identity there. It's just a little technical point. And if you're careful about how exactly a cotangent bundle is defined on a space that's a little pathological and on Hausdorff in this form, you do get exactly this geometry, the phase space that we found for this theory. If the word cotangent bundle doesn't mean a lot to you, it just means that if you start intuitively with this the space of geometries, the thing in the argument of T star, and then at every point there lives a space called a fiber, which is the cotangent space, which is in this case isomorphic to the tangent space. So for every point in these skeleton, that's like a comb of yellow and blue, the yellow and blue lines, the vertical directions represent the dilettante solutions, and those are the cotangent space at each of those points. The nice thing about having a cotangent bundle structure is that is quite amenable to quantization. When we have, now in the last part of the talk, when we have a phase space that is a cotangent bundle, then the Hilbert space is naturally the space of normalizable, square integrable, wave functions on the base of that cotangent bundle. In this case, the base is just this space, a space of geometries. So that is very convenient. Even though this classical mechanics problem was hard, the phase space has a very nice mathematical structure. This, however, is a bit subtle precisely because this is not a Hausdorff space, it does not inherit an integration measure from G tilde, and therefore it doesn't make sense how to talk about square integrable wave functions on that. So a better way to quantize that evades this problem is to start with square integral wave functions on G tilde, and then impose the remaining gauge symmetries, the adjoint and inverse action, at the quantum level. This also requires some care because the gauge group is non-compact, and then the usual Dirac quantization suffers a lot of problems. But there is a fairly well understood procedure for quantization known as group averaging, developed for mathematicians first and brought to the physics literature in the early 2000s, that is exactly designed to deal with non-compact gauge groups, which is often the case in gravitational theories. And so in my upcoming paper, I complete this quantization procedure by imposing the constraints at the quantum level using group averaging, or in particular, a renormalized version of group averaging that I introduced to make group averaging well-behaved. And as far as I know, this will be the first quantization procedure of de Sitter JT that quantizes the entire phase space, as opposed to just a subset of solutions. I mentioned earlier some people took particular gauge fixing conditions that reduce you to just a certain subspace of the phase space. They couldn't capture basically the black hole solutions in the quantization. This is, as far as I know, the first procedure of quantization that includes the black hole solutions. And just, of course, I don't really have time to explain this, but this is the solution I find from completing this quantization. The Hilbert space of physical states naturally splits into super selection sectors, one for the expanding and crunching solution, so these superpositions of geometries where the dilettante was expanding or crunching, a sector for superpositions of geometries that had conical singularities in the future and the past, these cones that we looked at, and then one sector for each n labeling the number of black holes. So that will be one of the main results of my upcoming paper. And with that, we are done. They disappear, basically. In fact, you kind of, through my renormalized group averaging procedure, you can choose whether to include them, but in any case, it would be separate super selection sectors. I did not include them there because usually when you start with square integrable functions of something, usually square integrable functions do not see measure zero subsets of the phase space, of the configuration space. Since square integrable wave functions usually are actually two functions that differ in a measure zero set are considered equivalent in the L2 space. We don't usually think about it in those terms, but there is secretly an equivalence relation there. So two functions that differ on the null subset, the subset where Q is null, are going to be the same. So these null solutions get washed out in the quantization procedure. There's a way to save them by just looking at that subspace on its own, which that requires some care, but I could explain more. But motivated by this getting washed out in L2 in general, I remove them. They'd be disconnected, yes, exactly. There would be additional super selection sectors which you may choose to include, and it's kind of unclear whether you should. But there would be separate sectors, indeed.
The singularity, if there's any sense in which they're resolved,
Yeah, that is a good question. I don't know. The states in this Hilbert space would look like superpositions of these geometries with a conical singularity at the future and the past. And if there's a sense in which there's a special superposition that resolves the singularities, I'm not sure, but that's a picture of this. It would vanish on the conical singularity, yeah. It would in this, certainly the value of the dilettante indeed would have a variance. In this particular case, I'm choosing to work in the position basis of the polarization where my wave functions depend on Q, not on phi. So then there's certainly a variance in Q depending on what state there's a variance in phi depending on how wide you define your wave functions on Q. If that makes sense, just position and momentum. They're in the quantum theory, the norm of Q and the Q norm of V have a canonical commutation relation. So yeah. Yeah. Yeah.
Classical singularity resolved in quantum mechanics with the energy eigenstate bottoms, right? And that
yeah. I think that's a very good question, and I think we need a slightly different machinery to try to answer it, because a way this quantization worked is that we started already with L2 of G tilde, so we're already parametrizing the solutions in terms of these global quantities at the norm of Q and the norm of V, and not so much in terms of as like wave functionals of the value of the dilettante field on a slice. That would be more akin to Wheeler-DeWitt quantization, where you don't impose any of the constraints at the classical level, impose them all at the quantum level. That type of more traditional Wheeler-DeWitt quantization would be interesting to do, so we can ask physical questions like that on split Cauchy slices. It is harder to work with because then we're working with a field theory. So then, for example, group averaging gives you path integrals, and so that comes along with the usual challenges. Whereas by imposing some constraints in the beginning, in the classical level in the theory, we evaded those issues by already working on quantum mechanics. But in exchange, we lost the ability to talk about wave functionals of the value of the dilaton and so on. And that is definitely a topic of further research that we've been looking into a little bit. Well, this paper is just me, but I've also been trying to think more about Wheeler-DeWitt quantization with Patrick Jefferson and Daniel Harlow a bit. Yeah, so there's definitely one more physical question that I think could be tackled in that more general framework, but it's still under construction. Certainly, that's exactly the idea. In the end of the day, it turns out that each of these leaves gives you a different super selection sector. And you might have guessed that in the beginning, at least like, okay, I can do integration in each of these leaves, so I'm going to quantize them separately. But if you just do that from the beginning, it's not so clear that these are super selection sectors in the full theory, and that, whether the full theory indeed split into super selection sectors. By applying group averaging to the entire phase space at once under a unifying framework, we confirm that indeed this split into super selectors happened. So if you were only interested in one of the sectors, you could have just done quantization on one of the leaves. But that wasn't obvious before doing group averaging. Yes, this theory is really simple in the sense that because it's a closed universe, the Hamiltonian is 0. So there's no notion of dynamics that are going to move us from one point to another in phase space. Again, in the context of Wheeler-DeWitt quantization, what one can do is introduce a clock. If we use the dilaton as a clock, at least in some solutions, not in all solutions can we use the dilaton as a clock. In the ones with black holes, the dilaton is not smoothly, monotonically changing, so it's not a good clock. But you could add matter, which we didn't here, that hopefully can serve as a clock in your space-time, and then define Hamiltonian with respect to that clock, and then ask for dynamics between points. That phase space is going to be a bit different because the space of solutions haven't included this matter, will depend on the specifics of the matter. But that's definitely an interesting question to look at, and something that people are very interested in. Include an observer that can serve as a clock and can give you some sort of dynamics in your universe and resemble more our experience in a closed universe. So it's definitely an interesting question that this pure JT, no matter JT, can't really capture because the only relevant notion of a Hamiltonian is the boundary one, which vanishes. So how to quantize? You want a bit of details of this group averaging? Yeah, so the idea is actually, let's see if I can say it. It's kind of intuitive. Let me see if I can explain it in that intuitive way. You start with a kinematic Hilbert space that just is a quantization of the unreduced phase space, like L2 of G tilde. It's a Hilbert space that contains more states than what you want. So if the gauge group is compact, you can just look at the states that are invariant under gauge transformations within the kinematic Hilbert space and keep those. And that's your physical states lived within the kinematic Hilbert space, and you can construct a projector to pick them out. That's how we pick them out. We construct a projector that reduces to them. Usually this projector looks like an integral over the action of the gauge group divided by the volume of the gauge group. Like if you start with a kinematic state psi, if I do this, act the unitary representation of the group, how it acts on the states, integrate over the group, then this state is invariant under gauge transformations by the Haar property of usually the groups are compact and Hausdorff, locally compact and Hausdorff, and therefore they have a Haar measure. Then if I act with another gauge transformation, it gets absorbed in here, change the metric, change the measure. And so we construct a projector, we should call pi, that acts on kinematic states in this way, and therefore, and then the image of this projector, written as pi, contains all the physical states. However, when the gauge group is non-compact, this integral is problematic because this volume is infinite. In other words, if you try to look at, more simply, if you try to look for states that are invariant under all gauge transformations within the kinematic Hilbert space, and your gauge group was non-compact, you're going to find no solutions. You're going to find that none of the physical states lived in the original kinematic Hilbert space. It's basically because you're trying to find states that solve this equation, where psi labels a kinematic state, not necessarily physical. You're trying to find psi for which this is true for all G in the gauge group. If you did, then such a phi would generate a finite dimensional representation, but your gauge group was non-compact, and so there shouldn't be any unitary finite dimensional representations. These are all different ways of saying that the problem when the gauge group is non-compact is that the physical states don't live in the kinematic Hilbert space. So you have to look at a larger space, usually a space of distributions on that, and find the gauge invariant states there. And that's exactly what group averaging is primed to do.
You can write a finite sum or countable sum.
Can you say that again? Sorry.
I say if you input space to another space, think about this infinite dimension integration as a finite countable sum.
No, not exactly. No, the idea is it evades this problem, and then what group averaging does in particular is construct a map, known as the Riggen map, from the kinematic Hilbert space to the physical one. So it does look like a map where you're taking in kinematic states and then outputting other states that live outside of the kinematic Hilbert space, but are gauge invariant from a Hilbert space, etc. And it also gives a prescription for the inner product. And this lies at the confusions and ambiguities around defining an inner product in gravity, which is that if you can't find your physical states within the kinematic Hilbert space, the kinematic Hilbert space had an inner product that came from the canonical quantization, like this procedure from L2 of G tilde that has an inner product. But if you have to look for your physical states outside of that, then there's a choice of what inner product you put on the physical states that you obtain, and that's what can give differences in different quantization procedures. And again, that's exactly at the core of the ambiguities around what is the inner product in gravity, which is a theory that suffers some of these pathologies. Yes?
Maybe to know enough about the my curiosity after quantizing a theory would be what is an observable, like what does an observable look like?
Yes.
Can you do this for this theory?
You can. It's a bit tricky. So in particular, when you do group averaging, you have to choose the domain of this Riggen map to live within the kinematic Hilbert space. You should pick a dense subspace. And the details of how we pick that subspace, the domain of the Riggen map, tell you what observables we have in the quantum theory. If you're familiar with the theory of rigged Hilbert spaces, or just simply like Schwartz functions and tempered distributions in quantum mechanics we work with tempered distributions and just sort of just wave functions. They come from using kinematic states that are Schwartz functions, which are just close under the action of x and p. And so that ensures that in the quantum level, x and p are quantum operators that survive the quantization. So depending on which classical observables you're interested in asking, you can do this group averaging in slightly different ways. And it will depend exactly on which computations you're interested in doing. There's no general canonical choice. It depends on which observables you're particularly interested in. And so that's like something you can ask on a case-by-case basis, but already using this formal procedure, which is well understood now. Hope that made some sense.
Like the middle, one of the space is something like the volume space, like something the dilettante makes it's not local.
Yes.
But before, with some integrated version of the dilettante is excessive cluster. So is that right?
Certainly, yes, exactly. That would. It's the classical observables would have to be gauge invariant, commute with all the G, and then so the classical level, those are the norm of Q and the norm of V. You can write those in terms of a single Cauchy slice. The norm of Q would correspond to an integral over the Cauchy slice, and the norm of V corresponds to a local quantity of the dilaton. Like you have a V up to maybe possibly a sign or well, how should I write this? Yeah, like V square, so like VI in the metric from the Killing form in the Lie algebra. So that's the Minkowski metric here. This up to maybe a minus sign I'm forgetting looks like this. Oh God, I think it was this. Sorry, this is in spacetime. If I read my signs correctly, this is equal to the norm of V, so that's something you can calculate in your locally at each point. So this is a classical observable, and then kind of Q and V are actually the simplest pair of classical observables that you might want to ask survive in the quantum theory. V is exactly the same. It actually turns out to be something, it's locally. That's right, yeah, so these are functions, but it actually are independent of which point in space-time you calculate it in. So it ends up being this locally measurable quantity. It's infinitely many. It would be any superposition of space-times where the dilaton is expanding or crunching. It depends on which polarization you pick. You can write them as functions of Q or functions of V, or functions of some other observable if you pick a different polarization, say of your Hilbert space. So the most natural way to do this is to choose the base of the phase space for your polarization, like position space wave functions. So then the wave functions, physical states are wave functions of Q, the norm of Q, and then V would be the canonically conjugate variable to that. So you could do Fourier transforms if you want to go to V space. So those are the simplest variables and the ones I consider mostly in the quantization. So there's indeed at the quantum level a notion of the norm of V or the norm of Q, but they come as canonically conjugate pairs. Did I answer your question? Ish.
To compare this combination, should we speculate that the result should be different and this method now currently should have a larger probable symmetry? So in this sense, I should have a more background to prove. So in this sense, I speculate that if I use these two combinations and to compute observable, I should expect a difference at the quantum rate.
Sorry, can you say that again?
Now you extend your space, and it seems that you have a bigger symmetry. So I expect you can include more background in your combination.
You don't have a bigger symmetry. So the idea is, in fact, that there are actually no states that were invariant under the action of the gauge group in L2 of G tilde. So the reason we had to go to a larger space is to find states that were actually, that respected all the symmetries. So we are not including new symmetries.
So in this sense, the canonical quantization still same with this combination.
Say again, the canonical quantization still?
Still same with this combination.
Still what, sorry?
I said canonical quantization still give the same answer to this combination.
Ah, yes, well, the idea is that this is canonical quantization, because the more old-fashioned canonical quantization in the sense of Dirac quantization would just say take square integral functions of the base of the phase space.
Yes.
But we saw there's no clear notion of what square integrable functions on the base of that phase space meant. And so that's why we needed group averaging, because the Dirac quantization procedure doesn't work in a straightforward way. So we need to impose the constraints at the quantum level. And then you can ask to impose the constraints at the quantum level according to different procedures. You can use group averaging. That's been shown. It's a special case of BRST quantization, so you could work with that, or more generally BV quantization, I think is what you're going to need for this theory. You can, so there's all sorts of different quantization procedures. There's a more general called refined algebraic quantization, which matches with group averaging when group averaging exists. But these are all choices of how to impose the constraints at the quantum level. And that is necessary in this theory because of the non-Hausdorff space of geometries.
Okay. Because actually,
So all of those are canonical quantization.
Peter West, his colleague, he used the best watch the street. And then he found the different he found all the symmetry in the watch the street without complication. It seems that the different quantities are different. And then if you use the best quantize, you can see the ODE symmetry that it does not appear in other quantization methods.
I see, interesting. Okay, I'll be happy to chat later and hear more details about that theory. Thank you.